Hey, in this video, I'm going to talk about plasmonic nanocrystal superlattice as metamaterial. Plasmonics involves a lot of interesting calculation for experimentalists or researcher who does actual optical measurement, whose expertise are not calculation, might feel it's too much calculation, and sometimes it's kind of difficult to know what is new thing, what is the physics behind the like measurement or new plasmonic interaction. This video is for people like that. So in this video, I'm going to talk about the basics of plasmonics, and I'm going to talk about why nano regime is important, what is the basics reaction, interaction between nanoplasmonic material, and in the end, I'm going to talk about why nanocrystal superlattice exhibiting plasmonic interaction is important for metamaterial. So when we talk about the plasmons, I always have to talk about plasma and the free electric sea. So basically, plasmonics is the phenomena that you can observe in the metamaterial, and in the metamaterial, as you know, electron can freely moving through, and sometimes people call it sea of electron because electron can freely moving inside the metal. Because of the freedom, when you apply the electromagnetic field or like electric field, the electron is going to be attracted to the positive side. So this is like something you always have to start when you study the plasmonics. And if you wanna think about the electrons more thermodynamical way, you wanna know the speed or energy of electron. So electron is like fermion, so the distribution function is always like this way, and of course energy contains the kinetic term, and when you calculate the velocity of the electron in normal metal, it's usually very fast, such as 10 to the 6 meter per second, which is not greater than the light of speed, but it's pretty fast number. So the electron is as free as that. And so now with this knowledge, we can understand what is plasma and plasmon. So plasma is not limited to the metal. So basically the idea of plasma is the state where electron is dissociated from nucleus of the atoms. But if you see it in macroscopically, they are electronically neutral. So this is the idea, and this is the reason why sometimes plasma is the subject of study for nuclear fusion, because the nuclear are not saved by the electron cloud, so it can get together or like closer than usual. So there are a lot of interesting physics going on in the state of plasma, but now we are a material chemist who's interested in plasmonic property or metamaterial. So in this case, metal can have the localized profile in the metals, because due to the effect of electronic field in the, for example, light. And in that case, you can say that because of the localization of electron, you can say that this is close to plasma, because electron is dissociated from the nuclear. And the suffix on means body. So if you take such a localization as one body, you can call it as plasmon. So here I put some example: electron, proton, or phason. If you study quasi crystal, one unit concept of unit of the phase is called phason. But like this, when you put on, you can, so this on in Latin means body, so you can take it as one state of body. So like this, plasmon refer to the small unit of localized electron, especially in solid. So this is the definition of plasmon. Of course, when you think about metal, you can take it as an excitation of the HOMO to LUMO. And here I put 4 most important examples of metals that can exhibit plasmonic property, and which is gold, silver, copper, and aluminum. And when you think the electronic configuration, you can find that always the LUMO is this S. So always the excitation of the excitation of the plasmonic material is D to sp band, except for aluminum. Aluminum has the LUMO of p orbital, so which is a little different. That is why aluminum has different plasmonic material than these 3. But the most important point is the plasmonic excitation can be also understood as the excitation of basically electronic orbital, like normal excitation. Well, this is the basic of plasmonics. So now I wanna explain there are 3 types of plasmon properties depending on the dimension of the material, which is bulk, surface, and nano phase. So I wanna start with the most basic one, which is bulk plasmon. So bulk plasmon is basically the idea is you imagine that you inject the light into the metamaterial, and you can imagine that the electronic field of the light is going to disturb the electron and change the localization of electron inside the bulk, right? And as you know, light oscillates like this way, and that oscillation can disturb the electronic profile inside the metal accordingly. So that is why the electron profile is going to be oscillate like this. And you might find that this is pretty close to spring motion. That is why sometimes bulk plasmon can be understood or calculated as the equation that deals with spring motion, which is the Rude model. And this is pretty simple, and if you think the spring constant, you can calculate the oscillation, which is this one. So basically this is called bulk plasmonic constant, and this is purely dependent on the material property, such as the weight of the electrons or the dielectric constant or stuff like that. Now this is the always starting point when you wanna think about the property of the plasmonic property of a metal. But when you study about plasmonic material of the metal, sometimes you might see the description of how to say the relationship between lusty appearance of the rusty shiny appearance of the metal and plasmonic property. And this surface plasmon mode is basically explaining the shiny stuff, shiny appearance of metal. So now we wanna think about not inside the metal, but the interface between metal and air. So the bulk plasmon deal with the the electron inside, right? But here we wanna talk about the electron profile on the surface of the material or metal that is exposing to air. And in that case, you can imagine that the electronic field, here now we have to limit the discussion to the EM mode, TM mode, which is transverse magnetic field mode. But anyway, you can imagine that the electronic field can create the electronic localization on the surface, and as a result you see this type of polarization of the electronic state. Sometimes this shows more negative because electron is getting together and the other part is getting more positively charged. So this polarization is what we call polariton. Again, on refers to the state of one body, and if you take this polarization, electronic polarization, as one body of the state, you can call it as a polariton. And so basically the idea is like this. So you can have incident light, and the incident light can interact with polariton, and the polariton, the interacted light is going to be dissipated after the excitation of the HOMO-LUMO gap, or sometimes just the light is going to be emitted. So this is why the metal has shiny appearance with a specific color, such as gold has golden color, yellowish color, because of there are two events like this. This is what we call surface polariton mode of the surface plasmon. And when it comes to the nanomaterial, the things are more complicated or more maybe simple. So you can imagine that, again, I'm going to talk about electronic field oscillation, but because the material, when you have a nanomaterial, nano is pretty small, smaller than the oscillation of the light. So again, the localization of the electron can happen, but in this case, all electrons can move from opposite surface to another opposite surface. And under the light illumination, the electron move always happening like a resonance. So this is what we call localized surface plasmon resonance. And this is going to show pretty interesting optical properties, such as the pretty characteristic color of nanomaterial, the size dependency of nano gold crystal or silver crystal, shape dependent. Another interesting point is when you think about the optical cross section, because of the resonance, this can basically attract more light than the light in the range of resonant. So if you want to study about this, you can study more detailed physics. But my point here is, when you have the smaller nanocrystal, many different interaction between material and light is happening, and that is why nano metamaterial is pretty interesting research subject. And another interesting point for nano plasmonic material is they can interact with each other. So when you have two nanomaterial when this has a localization, such as let's say plus, minus, the next one is naturally like to have minus plus because it has a more stable configuration. And if you write the diagram, energy diagram, you can write like this, which is pretty close to molecular energy diagram. And this type of interaction can happen. And in our field, this is called plasmonic hybridization. And so this is pretty interesting thing. And actually the plasmonic hybridization or plasmonic interaction cannot be limited to such a kind of similar positive interaction. My point here is there are two types of interaction. So when you have a strong absorption type of nanocrystal, there are interaction that can be categorized as Rabi interaction. But when you have a nanocrystal and that can have strong absorption for plasmonic resonance, but when you have another nanocrystal, maybe you can have a different shaped nanocrystal or different symmetry that can damp the excitation of the plasmonic resonance. There are interaction called Fano interaction. And this type of interaction can be quantified using the Rabi and Fano frequency. When you study the plasmonic hybridization between nanomaterial, Rabi and Fano pretty frequently appears in the paper, but this is the basics of the idea of Fano and Rabi frequencies. And when they interact with each other, many interesting things happens. But here are some example of optical interaction of nanomaterial. So one is Purcell effect. Purcell effect is pretty, the basic optical interaction when you have two material that are optically active and interactive. And this was obviously discovered by a researcher whose name is Purcell, and the idea is spontaneous transition rate of the nuclear magnetic moment coupled to resonant electronic circuit can be enhanced to the free space transition. So and the point is, when you have strong coupling, you have a small the spontaneous decay rate, but when you have a weak interaction or coupling constant, the spontaneous decay rate is going to be longer, which can be quantified by, for example, lifetime measurement or stuff like that. Another important the optical interaction is FRET. So basically this is the energy transfer system between two molecules. This can be used for biomolecular sensing, or it has a lot of important application ends. But my point here is, in the nanofield, the optical interaction is giving you a pretty special the consequence that can be used for the good materials. And lastly, I want to talk about why nanocrystal superlattice attract attention as a metamaterial. So I explained, the gold nanocrystal or nanocrystal with plasmonic material can have specific nanomode plasmonics, which is called localized surface plasmonic resonance. But when this is packed into the order of nanocrystal order array, which is called nanocrystal superlattice, there are only specific mode of the law of the excitation because of the plasmonic hybridization. So, but still it has a nano feature. So this type of material, firstly, still possess the property as a nanomaterial, but plasmonic mode will change from nano mode to bulk or surface state, creating the continuous collective plasmonic state. So that is a special thing for nano crystal superlattice exhibiting plasmonic material, because this can only so basically you can take advantage of nano and the plasmonic hybridization, and you can change the plasmonic mode. So people are studying by changing the size of the nanocrystal and observing the plasmonic material of the superlattice of the nanocrystal, changing the structures or stuff like that. So there are a lot of interesting stuff is going on. So this is why now the field get a lot of attractions or attentions from the people and the researcher. So hopefully you can understand the basics about plasmonics. You can understand the difference between nano and surface and bulk plasmonic mode, and you can understand that the nanocrystal superlattice is going to exhibit some special plasmonic properties somewhere in between nano mode and surface mode. If you have any question, just let me know in the comment, and thank you for watching this video. See you next time.